Good afternoon. Welcome to day 2 of Build. Is everybody having a great time? Okay. Thanks everybody for coming. This is the Maximizing App Performance Using XAML talk. Please fill out an evaluation form. One of Kieran and my goals is to beat the score of our PMs. So we're running for office and we need your vote. So the question I get asked all the time as a XAML guy is XAML performance great enough for my application? And the short answer is yes, absolutely. It's great enough for the desktop shell team. It's great enough for the Office team. It's great enough for all the inbox apps. But I like to answer the question with another question. If the XAML framework was a car, what kind of car would we be? You see here there's a Formula 1 racing car. That car has done everything to maximize and optimize for performance, but it's made a lot of compromises. It can go really, really fast, but it can only go around a single racetrack. It has no cargo space. It's really uncomfortable. It's hard to drive. It's hard to handle. You couldn't pick up your kids from the daycare in that car, although you'd probably be the coolest dad out there. So totally optimized for performance, and we're not quite this car. Or would we be a stretched luxury limousine? With stretched luxury limousine, you have high-end leather seats, you're in the back, maybe you have a drink in your hand, you're getting to where you're going in style, and you know, a lot of productivity or say comfort. But you're not in control. Somebody else is driving that car, and you're not going to get where you need to be as fast as you need to. So we're not quite that car either. Our job is to have a balance between great performance and great productivity. So I'd like to tell people, we're the high-end luxury sedan of UI frameworks. So high-end luxury sedan, you're very comfortable, great leather seats, you can get around, the performance is pretty good for most things you need to do. And when you need to, you can really mash on the acceleration. You can really accelerate really quick. You're not quite as quick as a Formula 1 race car, but you're considerably more productive and you're way more comfortable. So you can get a lot of stuff done. So if that's all true, why are we having this talk? So this talk, my job is to teach you how to push the accelerator, how to really maximize your performance of your XAML application. We're going to spend a bunch of time teaching you how to read your instruments using the tools built into Visual Studio. And just like with a lot of, a racetrack, there's some hairpin turns. There's some hairpin turns in our framework, and I'm going to teach you how to avoid those. There are also, there are people who like to just drive their car, and there are people who like to tinker and, change your spark plug timings to squeeze out the last ounce of performance. I'm not going to go into those kind of topics here, but I'm going to give you some pointers along the way and show you where you can get more resources. So my name is Mark Alcazar. I'm the engineering manager of the XAML team at Microsoft. And helping me out is Kiran Kumar. He's an engineering lead on my team with over a decade of performance analysis in XAML.
Thank you.
We'll be using a top 10 list of things to go through, and we'll be applying it, Kiran will be applying it, to an app that has some performance problems as we go along the way. OK, so let's get started. OK, so as I go through the top 10 list, I'm going to be using these symbols to denote what guideline applies to what performance aspect. So you'll see I'll use the CPU speedometer for something that's about improving CPU. I use a tire because good tires on a car can take you more places. Low memory usage takes you more places. It's kind of a stretch of the analogy, but work with me. And then there's a gear shift for responsiveness and the spark plug for expert techniques. So here's the XAML performance top 10. These are the things we're telling everybody to go do when they have a performance problem. I'm calling it racetrack ready. We're using this with internal Microsoft teams. We kept meeting with teams and helping them analyze their application. And we saw a lot of the same things over and over again. And we finally said, wow, we should write this down. So we'll be going through all these in detail. I've kind of bolded some of my favorite ones. Each application, there'll be different parts of this list that kind of pop out for your application. I'm giving you a clue. 6 and 7 will be huge in the demo Kieran will be doing. but really, you'll never know which one really applies to your app. So guideline number 1. So because mixed metaphors are my specialty, I'm calling this the Zen of performance. And there's this axiom that somebody told me 10 years ago at Microsoft, and it's still true today. It'll still be true 10 years from now. The fastest code is the code you don't run. What that means is you have to try and find a balance in your application. There's a balance between features and performance. If you see that pile of rocks right there, pretend that pile of rocks is your application, and you have a very feature-rich application. You add one more feature to your pile, to your app, and it falls over. It's hit that threshold, and the performance is bad, and nobody wants it. Or I could have the most optimized app in the world. I could take out all the features. It could just have a, start up and render to a frame buffer and show a green rectangle. So you have a single rock. And that's not an app anybody wants. It's not so useful. Kieran, you look...
Yeah, like you're going through all this analogy, but what does this really mean? What does this really mean to us? What does this really mean to these guys?
Well, that's a great segue. I'll give you an example. It's almost like we scripted it. So you'll see here, I call this Zen in practice, this example. So this is the phone 8.1 calendar application. And you'll see in the top right-hand corner, you'll see a symbol of the weather. So this is one of those apps that my team worked with that team to help improve the performance of. And how does the weather work? Well, it calls a location API. It figures out where are you. Then it does a network request to Bing. It gets back a chunk of XML, and it parses it, and then it decides what is the symbol it's going to show for the weather. And that takes a bunch of work. So when we profile this application with that team, we notice all this activity on startup. And we said, hey guys, really love the feature. I use it all the time when I'm picking up my kids or going to plan the weekend or go to soccer practice. However, the most critical thing for this application is to show your calendar appointments, because you want to know where your next meeting is, what do you have for your day. So we made a suggestion to that team, and we said, hey guys, how about you wait until the appointments are rendered on screen, and then after that has come up, then do your network request, and then do all that work. The user the user experience is almost exactly the same. The app has all the features it had at starting. However, it's way more responsive, and it starts up way quicker. So I thought this is a great example of Zen in practice.
That's great. Yeah.
If there's anything you get from this talk, this first, apply the Zen of performance. That's a hugest. I think it covers everything. Okay, so moving on. Guideline number 2. Define your target and your goals. A lot of performance problems start up as, it's slow. Well, what is slow? Is it your app startup? Is it you're using too much memory and it's not fitting on a phone? Is it the scrolling is laggy and it feels awful? And then once you've defined the problems, define some goals and measure them and track your progress towards your goals. Kieran's going to go through this when we start showing our demo of our tools. And we haven't seen our application, which has all our problems as yet. But in general, we're saying try and start up within 1 to 2 seconds, target memory usage under 50 meg, and try and have responsive scrolling. Guideline number 3, convert to a universal Windows app. Why? In this release, my team has done a lot of work to optimize XAML to meet the performance needs of the shell and all the inbox applications. And a lot of our optimizations are only enabled for Windows 10. For example, in Windows 8.1, we had a binary compressed markup format, so we compile your XAML to a compressed format. And in Windows 10, we've done a lot of work to optimize that format even further, and that requires a recompilation. And as we go through this demo today, as we go through this talk, we'll be showing you a lot of new features that are only available for Windows 10, such as x:bind and x:"defer load strategy. So how much are the gains we see? So these are some of our internal test apps we've been using to measure our gains with. We're seeing CPU improve up to 30% and working set up to 45%. So really some huge gains. It varies by your application, but you kind of get it out of the box when you convert. There is some, pain on conversion, and I know Sam Jarwan is going to be giving a talk tomorrow about how to have a multi-headed Windows 10 and Windows 8.1 app, and so that's a great talk to go see to learn about how to go do this easily. Guideline number 4, profile your application. See if there's a problem with your code. Use the inbox profiler, and then use Visual Studio to do the analysis. So we'll be going through these tools in detail. VS now has an awesome timeline tool that shows you your CPU usage over time. There's a profiler, standard code profiler, to see the hotspots in your code. There's a memory usage tool that shows your memory usage of your app over time. And then we have our new visual diagnostics tool, which is great for you understanding the structure of your app at runtime. So now Kieran's going to step in and start doing a demo showing VS and our tools.
Thank you, Mark. So first thing first, let's go and take a look at your app and see what kind of performance problems are we talking about here, right? So let me go ahead and launch your sample app and see how it looks.
Well, we said it had a performance problem, right?
But it should not be that we need to go for a coffee here.
Okay, it's
Okay,
coming.
finally, it came up. Sounds good. Looks a pretty simple app to me, Mark. Here, it's a typical master and detail layout here. I have a list view on the left side. I have a main page on the right side. And it does navigate to another page. So pretty simple app to go look for. List view with 2 pages, right? So with any performance analysis, the very first thing which I always advise is to go collect some traces, right? So once you have the traces, then go list those 5 bottlenecks in your application, looking at that traces, and then go one by one into those bottlenecks and see what you can find and optimize, right? So what I'm going to do here is going to show you how using Visual Studio 2015 you can start capturing those traces and also analyze those traces at the same time. So we have an awesome dashboard which we introduced in Visual Studio 2015, which will help you capture many different kinds of traces. My favorite one is here, the one which is called timeline view. The reason the timeline view is so interesting is because it gives you a very high-level overview of what your application was performing and how it was looking. So all you have to do is check the appropriate check mark there and then click on the start. So as soon as you click on the start, Visual Studio is going to launch your application, and in the background it's going to start collecting your traces. So you basically wait for a point where you think you have enough traces collected, and you close your application. Once the application is closed, the Visual Studio is going to land you directly to the timeline view. The collection of traces is a little time consuming, so what I have here is a pre-canned trace which I'm going to pull in. But what you're going to do is, as soon as you close your application, the Visual Studio is going to directly land you to this page. So this is what we call our timeline view. So in this timeline view, you have 3 main sections. The top section, what you see here, is the basic timeline view of your application from the process start, which is extreme left corner, to the point where you actually closed your application, this is the extreme right corner, right? And then you also have bars indicating individual events occurring in your process. And each bar is color-coded to the unique event. So when you hover over that bar, you know what kind of event that was. Like for example, that green one, that whole section of bars are devoted to your application code or app code running. And if I hover over in this section, you can see some layout was happening in that time. If I hover over to another section here, it tells me that rendering was happening at that time. So each bar is also indicated in this table to designate what particular time that particular event has occurred and how much time that event was taking. So it's basically a very interesting tool for you to go play around with to see what events were taking how much time, and you can figure out that bottleneck that you are looking for. So since we have seen our application has a startup problem here, so what we are going to do first is to figure out what our startup time actually looks like. To see or to define any timeline, you need 2 markers. You need a start marker and you need an end marker. For our application, it's very simple to define our start marker. Obviously, it's a process start, which is going to be the extreme left corner. The interesting thing is, what would be our end marker for our startup time is? Now, it's completely defined by you, because you are the app owner. So you define, for example, for our app, we assume that our end marker is going to be when our list view and the main page was up on the screen. The frame which was represented or which was responsible for creating that image on the screen was our end marker. Now, how do I figure out that end marker? So here I need to give a basic description of how platform works when a XAML process runs. So platform divides the whole processing of startup into 3 main buckets. You have parsing, you have layout, and you have rendering. The parsing is when the platform consumes your XAML and creates your element tree or the UI tree of objects. And then it passes that UI tree to your layout. The layout engine runs through that tree, defining those positions for those UI element, where each UI element are going to be placed with respect to their panels on the screen. And then that whole tree is passed to your rendering engine. The rendering engine then goes through that tree and starts creating those rendering instructions, which finally gets pushed into your hardware and gets to the screen. So what we are looking for here is that final rendering engine process, which has created that scene to get to your screen. So I know that I have a list view and main page, which eventually is going to create a lot of layout elements. So I'm looking for this big layout event here, which I'm assuming is the one which was responsible for creating my list view and main page. So I'm going to look for a subsequent rendering event after that that looks like here. So that would be my end marker for my whole startup. So I'm going to do is I'm going to select this whole region to see what my startup time look like. Okay, so looks like, Mark, we have a startup time of almost 12.5 seconds. And our goal is to be within 1 second.
Okay.
That's a pretty long way to go. Let's see if we can do that in the next 60 minutes. Right?
Okay.
Okay, so the first thing what we should do is go figure out what our bottlenecks are. So why don't you start taking notes here so that we can go through that notes when we are going through our slides, right?
Okay, got it.
So, okay, so let's take a look at, so first thing was the startup time. We have obviously 12.5 seconds as our startup time. And I have an awful lot of time spent in my app code here. So I need to go diagnose that. So I have around 6 seconds spent in my app code. I'm going to figure out why it's spending that much time. I have a gap here where nothing is happening. That's very interesting. So that's almost around 1.5 seconds of gap. I need to go figure out what is happening there. I also see an awful amount of time spent in layout, almost 3 seconds. That is, you can see it here. That's like 3 seconds time spent in layout. The interesting thing is, Mark, I see awful amount of elements created. You see this number inside this parenthesis around the element? That's the element count, the elements created during that event. So like, for example, here, when the layout pass was happening, it was applying templates and then creating those elements. And we have 4,000 or 4,600 roughly elements created during that layout time. So that's an awful amount of elements which we should go fix, right? And then I also want to see what our memory looks like for this application, Mark, because memory is also important. So I have a can trace for memory also here, which looks something like this. Again, it's the same process. You go to your dashboard, check the memory, start your application. Once the application is stable, you close your application, and you're going to land to this page. So if I hover over this graph, it shows me that we are around 82 megs. Our goal is 25 megs, right? So we have a lot of work to do, Mark.
Okay.
Let's keep going.
Okay.
Come on.
Okay, hold on. Okay, so while Kieran was talking, I started writing down and collecting all the stuff we have to do, so hopefully we'll get there.
I hope so.
Okay. Okay, so guideline number 5 is about deferring work on startup. So a lot of apps do a lot of work on startup, and we also need to do, the framework needs to do a lot of work on startup. And what we recommend, as soon as you can, as much as you can, do all your initialization off thread, because we're just more efficient that way. And then while you're doing your initialization, you need to show some form of in-progress UI. The app Kieran showed, the slow app, sort of came up. You see like the list view hadn't quite rendered its contents yet, and it just feels like it's hung. And that feels very unresponsive. So both try and go off thread and let the user know you're doing something. Guideline number 6 is one of my favorites. It's huge. So it turns out our framework isn't magic. When you have a bunch of instructions in XAML, a bunch of elements, we need to do work. We need to go parse it, as Kieran was saying, parse it, layout, render, and that takes a bunch of time. So the rough guideline I tell people is think in terms of every 1,000 elements is roughly a second. It's not quite that bad, but it's roughly think in those terms. So if your main page of your app is 10,000 elements, it's going to take about 10 seconds to parse and render that app. So so just think about that. So the big guideline is, hey, reduce the number of elements on your critical paths. We tell people, hey, just look at the total amount of elements you're creating at startup. It's very easy. In your resource dictionaries, you have a bunch of styles, maybe stuff you're not using. You develop your app over time. Just trim that down. If you don't need it, just move it out. And then we'll talk a little bit about templates and repeaters. Templates have this multiplicative effect, so look for that, creating an element explosion. So it can be painful, trimming your markup. The good news is, in Windows 10, we've introduced a new feature that makes this very easy for you to go do. We're calling it X:"defer load strategy. It's a new XAML construct that tells us to, hey, delay instantiation of this part of the tree. We're seeing a lot of people use MVVM as a design pattern in their apps, and a lot of MVVM apps have a Boolean to visibility converter, and they turn on and off parts of their UI. So we suggest, if you're doing that, use that in conjunction with X:"defer load strategy. So how does this work? Here's a sample in markup. I have a stack panel with a name on it, and I'm saying X:"defer load strategy equal lazy. So that's an instruction to our parser saying, hey, when you encounter this, just read over this element tree and don't create anything inside. Later on in my application, when I need to instantiate that object, that tree, I just do a find name on the named additional product page, and that whole subtree gets instantiated. Very powerful, very simple. It's a huge gain for performance. OK, so Kieran's going to now take over and apply some of the things we just talked about.
Thank you, Mark. So I really liked your idea of the progress ring, right? The reason is pretty simple. The application which we saw really was very slow. It not only was slow, it was not talking to the user. When I say talking to the user, it was not giving any feedback to the user. So what normally happens in that case is the user gets frustrated and goes to Task Manager and kills your application. You don't want that to happen. So it's very important that if you can't fix the startup problem because you have some strong dependency on something, at least provide that perceived experience. So what I have done, Mark, is went ahead and added this progress ring to my application. So at least now when the application is starting up and taking 12 seconds to get to our page, we'll at least get a progress ring. The user will be, OK, the application is doing something, right? You're not going to get frustrated and start closing your application. OK, so let's go take a look at our trace again. Now, I have the compiled version of your app in Windows 10, and I took the trace again on that one. It looks very similar to what we had before. So let's go one by one. So our first problem was our app code here, right? So I'm going to go select this region and see what kind of events I'm going to see in my timeline tool. Interesting. So I don't see any informative information here to go debug anything because, yes, it is doing some garbage collection, but that is not something which I did in my app. That's the CLR runtime going and doing. So it's not really helping me anything. So this is where I need to get some assistance from my another trace. So what I have done is I have created or collected another trace, which is a CPU trace, along with my timeline trace, because I want to know if my timeline trace is not giving me something, what is happening in the CPU. So I have another trace here, which is CPU and timeline together. Again, it's the same thing. You go to your dashboard, you check your timeline, you check your CPU, you start your application, close your application, it lands you to this page. So if you see here, the interesting thing is, even though the timeline tool is not giving you anything, I can see the CPU is churning. That's the good news. The reason is because from the CPU, I can go figure out what stacks looks like, and I can go see what is happening in my application code. So let me bring the CPU stacks here to see what CPU is doing. Interesting. So it looks like, Mark, we have some kind of loop or iterator which is going through some kind of settings. So let's take a look at the code to see what is happening during that time. You see here, Mark? Mm-hmm. Right? So let's take a look. Settings.cs. Let me hunt for that iterator somewhere here. OK. So it seems like this is the one. Let's go read this code, Mark.
OK.
So it looks like you're trying to load something from the disk. That's good. So you load the XML file from the disk, and you're trying to iterate through your local store collection. And your comment here says, iterate local store and find the first top-rated item from the first store. Awesome. So you're going to pull the first store. You're finding the top-rated item from your first store. If the item is valid, you're setting it to your return value. And then you're breaking out. So that seems, wait, am I looking at the right one? OK, so there's a glitch in the demo. I'm sorry, this was not supposed to be here. But I'm really sorry about that. Okay, so the glitch, the trace was basically like, okay, if the break was not there, so just play along with me here, I'm sorry. So the return item is set on this, and then I see that your loop is not returning, and it just keeps on going through the loop. So that was the bug. So basically, I'm going to put that break here again. So what this will do is it's going to break out of the loop, and we're not going to see that CPU churn anymore.
So you're saying there was a bug in my code?
There was a bug in your code, and I went and fixed it, and then I forgot to remove it after that.
Okay.
Okay, so that should basically take care of our thing in this mark.
Okay.
Right? So let me go back and see what I have in this. Can you do me a favor, Mark? Can you go back to our slides there and show me what I have is as my second item there? What do we have as second? Sorry, we have.
Oh.
Okay, so sorry. Let's go back. Go back to my. I'm sorry. Okay. So let's go back to our traces here. Okay. So now that we have taken care of our app code CPU utilization here, so next what I want to do is I want to go look at what is happening in this gap. Right? So whenever I see this gap mark, the thing which goes into my mind is there is something which is not churning. Either CPU is not churning or we are basically waiting on something. So let me go take a look at my CPU trace here and see what is happening during that time. So in this time, I see that my CPU is also not churning. So that's a pretty clear indication to me that there's something in the app which is waiting on the network. That's the first thing which goes into my mind. So is there something in your app which is waiting on the network here?
Yeah, I think I added a feature to, it shows in the top right-hand corner the users who are also looking at the same item.
Okay, okay, okay. So is there something which is important for your first frame?
Probably not.
So it looks like the same example as your weather one.
Yeah, almost.
Right?
I guess I didn't follow my guideline.
Okay, so let's go take a look at your app and see what is going on there. So let's go back to your code here and see. Okay, so you're initializing your settings. That's good. So you're loading from your disk. This is the code which we looked at before. And then once you load the data from your disk, you're initiating your live data request. Sounds good. So when that packet is received, you are actually going and updating your main page and list, and then you're updating your live data, right? So what is happening here, Mark, is you are actually waiting to update your main page and live data until your live data arrives.
Right.
So what we really want is our main page and list to be updated before the live data arrives, so that it's in parallelized, right? So that you can reuse that gap, and then the UI thread is free to do the additional things there. So what I'm going to do here is I'm going to just copy this code up and making sure that as soon as our disk, the data from the disk is loaded, we have enough data and information to populate our main page and list view. So that's what this code is going to do. So once we have this being pushed to our UI thread frees up and starts churning and starts rendering our main page and list view. And in parallel, we are going to receive the data from the live, and then we are going to update the live data. So I'm going to comment this out. So that should fix the stuff which we are talking about, right?
Got it.
So let's go back to our trace here. So this should be fixed, and this should be fixed, right? So the other interesting thing which I really want to talk about is the element count mark, right? So element count is extremely important for your startup experience or startup performance. So one thing which you need to understand about element count is the number of elements which you're creating during your startup should be same as the number of elements which you're seeing on the screen. If there is any element which is created and not seen on the screen, you should make sure that it is deferred using your deferred loading strategy. Otherwise, you're paying for the elements which you really don't want. Now, the question is, how are you going to figure out, how are you going to diagnose those elements? So this time around, we have an awesome tool introduced into Visual Studio 2015, which will help you do this. So I'm going to bring that tool up. So under debugger, under the debug menu, you have Windows. Under Windows, you have live visual tree. So what this tool is showing you is the live representation of the visual tree of your running app here, right? So if you look at the app, it seems pretty simple to me. It's you have one single page, maybe a panel to hold your image and 2 text blocks here, and then you have a list view and you have a main page here, right? So we should try to coordinate or correlate those elements to our live visual tree here. So let's start digging into this. So I have a main page here. Sounds awesome. I have a stack panel. I have an image which corresponds to this image. Good. I have another stack panel. I have 2 text blocks which corresponds to this image, this text block, and this text blocks. That's good. So far we are paying for the elements which are there on the screen. Awesome. Then I see this. What is this, Mark? I don't see anything related to error in this page.
Yeah, I added some UI, so if I got an exception, I could throw up the error.
So is that something which is going to be always there? Looks like it's an error condition, right? So error condition, majority of the time your app is not going to be in an error condition.
Well, I hope not.
Yeah, so it seems like this is a great candidate for our deferred loading strategy, right?
Yeah.
We can defer that and not pay the cost of that error canvas when the application is starting up. So that is one thing, right? So let's keep digging on this one. So we have main panel that I believe is holding our main page and this list view. So let's keep going. So our scroll viewer looks like this guy. Then I have my details items page that seems like this guy. So let me drill into this. Okay, so I see 2 pages, Mark. I never navigated to my second page, yet I'm paying the cost of second page, right? Looks like for performance optimization, you preloaded that page.
Yes, I wanted to make sure the switching was really quick.
Well, our platform is not that bad. It should be able to parse that much and get it on the screen. So what I would suggest is, let's go and defer load that too. So with 2 things in our list to defer load, let's take a look at our code and see how we can defer load those 2 things, right? So let me bring up first my details page here and see what our XAML looks like. So I have 2 stack panels, one for the main details page and one for my additional product page. So this is the one which I want to defer load. So all I have to do for defer loading is cut paste this. And that should do. Now the tricky thing is this. By doing the defer loading strategy and putting the defer loading strategy into my stack panel, what I have told my platform or told the framework is that the stack panel and anything underneath that should not be created as part of your startup. It should be deferred until the app explicitly goes and asks for it. So what is that explicit event which is going to go trigger this? That's an interesting question. So let's go take a look at code behind for this. So all I have to do to go and realize that tree or realize that element is this, find name. As soon as I do a find name on that stack panel, the platform goes and creates that stack panel, all the elements underneath that, lays that out, and then renders it. So this is how you go and defer load the stack panel, and yet won't pay the cost during your startup. So we had one more thing to go look at, Mark. So let's take a look at what that was, your error canvas, right? So let's scroll into your main page and see where your error canvas is. OK, here. So let's see what we can, here. You see this visibility collapse, Mark? Mm-hmm. So anytime I see visibility collapse, that's a red signal for me. Like visibility collapse means app author knows that the visibility of that element is not going to be visible when the application starts up. If it is not going to be visible when the application starts up, then why create it, right? So that's another interesting one which we can go and defer load. So while I fix this app, Mark, why don't you go with the next set of slides here?
OK, great. So repeaters, the next set of guidelines apply to repeaters because we see this over and over and over again in XAML apps. So guideline number 7, another huge one, is to use virtualization. So the great thing about XAML is how easy it is to do data binding. And out of the box, both list view and grid view virtualize, right? Meaning we try and create only the elements we need to be visible at that point in time. So if you have 1,000 item data collection and you're only seeing 100 visible, we're only going to create the items, the list view items for those 100. So that's great. Unfortunately, there are a few hairpin turns, a few pitfalls that you can go fall into, which disable virtualization. 2 of the most common ones I have there are putting a list view or a grid view within a scroll viewer. And it's a little unfortunate. It's a consequence of how our framework works. The scroll viewer tells the elements underneath it, hey, you don't worry about your size. Everything is infinite. You're in an infinite world. And the list view says, wow, I'm infinite. I don't need to virtualize. Gotcha. Another common one is you can change the panels. You can restyle retemplate the panels used in a list view or grid view. And the panels we use by default are virtualizing panels. I think virtualizing stack panel and items wrap grid. If you restyle list view, grid view, you can also disable virtualization. So this is a really important hairpin turn for you to know about and know how to look for. Guideline number 8. Again, data binding is widely used in our framework. It's about optimizing data binding. So the first part of this guideline is about simplifying your data templates. Data templates have this multiplicative effect. And it's very easy in XAML to have some redundant elements. You know, things just you develop your app over time, you know, extra stack panel, extra grid, all this kind of adds up. It's easy to sneak in there in your data template. Most of the time, it doesn't matter. You have a few extra elements on your startup code path. Who cares? Now, if you have it in a data template, it can add up. So for example, say you had 10 extra redundant elements in your data template, and you have 100 list view items shown on screen. 10 times 100 is 1,000. And if you remember the initial ballpark I gave you, that's 1,000 elements is roughly a second. You know, that's a second you didn't need. You just added it. So simplify your data templates. The second part of this guideline is use x:bind for data binding. And what is x:bind? x:bind is our new Windows 10 feature. Historically, our binding has been a performance bottleneck. And x:bind, we're doing more of the work, so it's all compiled code. So we're doing more work at compile time. And it's a huge optimization for both startup and memory. There are lots of other great benefits, one of which it's strongly typed. You try and data bind to the wrong object, and you get a compile error. So this has been a huge problem for our framework, and we finally fixed it. And then because we're code-genning all this code, you can debug it. You can put a breakpoint on the code-gen code and step through it, which is awesome. So here's an example of x:bind in practice. Historically, I would have a data context here, somewhere up there above this object. Now I specify a data type. So I tell the compiler, hey, everything beneath this is using this and this data type. So I'm using an interface right here. And then in the text block, historically, I would have said curly paren bind title. Now I say x:bind title. So we're code-genning at compile time, setting the text property to iitem.title. Huge for performance. So data binding is a pretty deep topic. This is one of those spark plug timing things I didn't talk about. So there's some additional features. So in 8.1, we introduced the container content changing event, which allows you to control how items get created while you data bind, and you can recycle items in your list. It's a great performance optimization, but it's a little hard to use. In this release, we're introducing a markup version of that. We're calling it x:phase. Sam Spencer gave a talk on this yesterday. If you missed it, I really recommend catching up online if you're doing a lot of data binding, because it's a very deep topic, and there's a lot for you to learn about it. OK, so Kieran's going to apply the next set of stuff we talked about.
Thank you, Mark. So Mark, while you were going through your slides, I went ahead, recompiled our application, and I collected the new traces for that. So as you can see, we don't have those big app code bottleneck and our network load bottleneck anymore, right? So with this, let's go do the same exercise of figuring out what our startup time looks like now after getting rid of those things, right? The same thing we are going to do. We're going to look for the layout, which was responsible for creating our list view on the main page. And then we are going to look for that next rendering event after that. So that should be our end marker for it. So let's go select all the way from our process start to our end marker here and see what our startup time looks like. So we are almost at 3.75 seconds mark. We went down from 12.5 seconds to 3.7 seconds. So we don't have to go for coffee anymore.
OK.
So coffee is canceled.
We're getting there.
OK. So let's take a look at what we can do for our layout now. So we are still spending a lot of time in our layout. So let me go select the layout portion here and see what is going on. So our layout is still taking almost 3 seconds there, right? So the other thing which I want to really point out here is there's enormous amount of elements getting created during layout, almost like 4,600 elements. So whenever I see that that many elements getting created in layout or parsing or any time, the thing which really goes into my mind is maybe the virtualization is not working for our app. So let's go take a look if the virtualization is working or not. So the great way to look at whether the app is virtualized or not is to go look at our visual tree, the live visual tree using our visual tree diagnostic tool and see how it looks like. So let me bring that tool back up here. So I have this app running here. So I'm going to resize so that it can fit in one screen. And let me bring that back up. Okay, so a couple of things I want to point out here, Mark. So one, I want to show that the defer loading strategy which we added for 2 of our elements, it does work. So if you see here, we don't have that second page anymore, because we did add the defer loading strategy. So during startup, the framework is not going to create that whole tree. That's why I don't see that here. Also, we used to have error canvas here, somewhere here, and I'm not seeing that either, right? So that means our defer loading strategy for those 2 things are working.
That's great.
So let's take a look at how our list view is performing in this case. So let me keep drilling into this until I get to my list view here. So this is good. I have a scroll viewer. I have a content presenter here. Let me go in. Item stack panel. So list view item. Great. So we are at list view right now. So thing which I always look for in my list view is how many list view items is my list view creating. If you look at this page, all I want to see is 1, 2, 3, 4, 5. And the platform, by default, if it's virtualizing a list view, would create 2 page worth of caches. So maybe at the maximum 12 to 15 elements, or 12 to 15 list view items is what I should be seeing in this. So let's see how much we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the list keeps going. It keeps going. So obviously, looks like we are not virtualizing here, Mark.
Oh, who knew?
Okay,
Gosh, I guess I'm not
okay.
following my guideline again.
Okay, so it looks like we need to go look at our code to see what's happening there. That's another interesting thing I'm seeing, Mark. You see this number here? So this number 14, that represents how many elements this list view item has underneath it.
Right.
So if you really look at this UI, see this UI, how simple this is, right? So this UI shows me that I should be paying the cost for an image, a text block, a text block, a text blocks. That is 3 text blocks, an image, maybe a panel, maybe 2 panel, or for you, maybe 3 panels, right? So maybe 6, okay? But we have 14 elements there, Mark. What are you doing? Let's go take a look. The reason it is important is, Mark, because these are repeater scenarios, right? Even a single element saving in the repeater scenario is a tremendous amount of saving, because you're going to save 1 in one list view item means it will be replicated for all the list view items. So it's extremely important when you're writing your data templates for your list view item, pay trouble or triple attention to the number of elements you're creating on those. So let's take a look at your code and see how your data template looks like for this. Okay, so we have the data template here. We have a grid. We have another grid. We have stack panel and another stack panel. So this is obviously is like something which is not right, Mark. A pretty simple thumb rule is this. If you are using a grid, think the grid as like a table. If you're using a table inside table does not make sense, right? Table is a table. So grid inside grid, right? So most of the time, if you're using a grid, you should be able to create a most complex layout possible just with using a grid. You just need to spend time, right? It's not a quick and dirty thing, right? Spend some time and see if you can really save some elements here. In this case, I should be able to save 1, 2, 3, 4 layout panels out of that.
Yes.
Maybe one additional panel we can add to that, right? So there is a lot of savings we can do here.
And I think if you saw Joe's talk also, you know, there's a new relative layout panel
Yes,
that people
exactly.
can also go use to
Exactly.
create complex layouts.
Exactly. So relative panels also a great example to use here to reduce number of elements here. Okay, let's keep going. Okay, so we have 1 text block here. Good. We are supposed to have 3. I'm keeping count of this. So 1. We have 2. Makes sense. We have 3. So we should, okay. We have 4. We have 5. And then we have this sneaking rectangle here. What is this doing here?
I can't remember. You were supposed to give me a code review, remember?
Okay, now blame it on me.
I think it's your fault.
Okay. So obviously we can get rid of this rectangle. Looks like somebody did not do the code review. Fine. Let's get rid of that. Let's talk about these 2 rectangles, Mark. So what is this about? Oh, again, my favorite one. Visibility collapsed, visibility collapsed.
I think it's an optional text I was going to put on the list view item.
Interesting. We see this kind of pattern a lot. you see a data template, and we see the app authors putting a lot of elements into their data template, assuming that, oh, for some of my list view items, these elements are important, so I'm going to collapse that for some and expand that for other. But here's the interesting thing. As soon as you add this, you're basically paying the cost of both of these text blocks on every instance of that list view item. So that is not going to scale for you. So interesting thing what you can do here is use defer loading strategy. So wherever you have your code behind to toggle your visibility, instead of toggling visibility, you do a find name on that, and it's going to toggle you for you by default. So basically, by doing a x:\defer strategy on these text blocks, you're going to save the cost of these two text blocks for all the list view items which really don't need these two text blocks. So that's going to save you a lot of elements, Mark. So I also see a lot of use of binding here. So I do want to go ahead and use your binding or x:\bind and see how it looks like, right? So there's a lot of work for me to do here in another 5 to 10 minutes. So I'll go ahead and do all those fixes for you, do my code review on this, and then go see how it looks.
Much appreciated,
okay?
Kieran.
Thank you.
Okay, so moving along, we're on our home stretch now. So guideline number 9 is about optimizing your images. We see a lot of applications use some very high quality images at times, and these can be several megabytes, and that can use a lot of memory. Most of the time, our framework tries hard to optimize it. So we try and only decode to render size. Sometimes we get it wrong. So what I'm telling people is the most optimal thing you can do is to resize your images in a design tool, if possible. If not possible, explicitly use the decode pixel height and decode pixel width on a bitmap image to say how big it is, and then we will optimize that memory. So here's an example in code. This is in my data binding source, and I'm explicitly setting a decode pixel height and decode pixel width. Or at least I hope I am. Okay, so guideline number 10 is about optimizing text rendering. So by default, Windows 10, we've optimized our text rendering code path up to 50%. And most of the time, our text rendering performance, it's not going to make a huge impact on your app startup. However, in a scrolling or data binding scenario where you're moving up and down, that's a lot of text, and we're drawing all of that as you pan up and down. So 50% is a big deal. There's certain typography features that disable our optimization. So I've listed them out here. The good news is you don't have to struggle too hard to figure out whether this optimization is on or off. We've added a debug settings flag. Is text performance visualization enabled? Thank God for IntelliSense. So you set this to true in your app, and then all the text in your app will render in a bright green color if it's on the optimal code path. So our recommendation is, particularly in data-bound and text-heavy scenarios, turn this on, make sure all your text is in a bright green, and if it's not, start looking at if you're using any obscure typography type features, and then turn those off or reevaluate. Apply the Zen of performance. Okay, so hopefully Kieran's ready for me. So we're on for the next demo. He's going to apply all the stuff we've talked about.
Okay, I want you to pay attention to the screen, Mark.
Okay.
What am I seeing there?
I think that's a scroll view.
Aha. So how did we miss this?
Oh, yes. Okay.
So this is the thing which was causing your virtualization to break.
I see.
Okay. And who are you going to blame? Okay, fine. It's fine with me. Okay. So let me go ahead and remove that, because that was the reason why our virtualization was not working, Mark. Like we have so many elements created because it was inside your scroll viewer. And as part of one of your slides, you tell we should not have our list view within our scroll viewer. So let's go ahead and remove that. So another interesting thing which you mentioned, Mark, was about text rendering, right? So I really want to see how we are taking advantage of fast text rendering code path. So what I'm going to do here is I'm going to turn on my debug settings for my text rendering code path to see how my text rendering looks like. So by default, I assume you did the right thing. We should see our entire screen worth of text turn green by turning on this, because green means we are going through the fast path. So let's take a look, Mark. Okay. Okay, I see all green, Mark. Do you see everything green?
I don't think the left-hand list view is green.
Okay, so we have a problem here, right?
Yeah.
So let's go take a look. So obviously, we have some problem in our data template to see why our data template or text blocks in our data template did not go through our text fast path. So let's go review our data template for our list view items here. OK, so this is the text block. That code looks good. This looks good, looks good, looks good, looks good. What is this?
I think the designers were editing my app.
OK, so last time it was me. Now it was designer. OK, who else? Your PM, maybe? Maybe next time?
We'll get there.
OK, let's keep going. Let's keep going. Let's get rid of that. OK, I have everything else looks good. Looks good. Looks good. So you did understood, Mark, right? Like, no, that was one of the properties which is whitelisted properties for us. So once you use that property, we are going to fault to the slow path. So we want to make sure that all the properties which we are using in the text block are the listed properties which we can support to go through the fast path. So by removing that, now I'm ensuring that all my text code is going to go through my fast path, and it's going to improve my startup performance on that, right? So with this, I do also want to go talk about the memory. Right? So when we talk about the memory of an application, the biggest contributor to the memory is images. So I'm sure Mark would have done the right thing for the images and would have decoded those images to the right size, because we have small thumbnail images. Right, Mark?
I got those images from Microsoft Marketing. And
I love those images.
And they were very, very proud of their high-quality, multi-megabyte images they gave me.
OK, and I'm sure you have right code there to decode it to right
I think I did. It was on my slide.
OK, after looking at your code review, not doing the code review, and then the other things, your PMs not doing the job.
OK, well, let's see.
Let's take a look. OK, where is it? Where is it?
Oh.
Aha.
I guess I didn't.
You do have that code here, but looks like you're trying to please someone, and then you just commented that code.
I forget I was playing with something or debugging or preparing for this talk.
OK. OK. So it looks like you were trying to demo this too.
I guarantee this is the last bug that Kiran.
OK. 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 Let's go comment this out, and then uncomment your original code here. I'm sure this was to please our marketing people, to show them the demo.
They wanted to have high quality. OK.
Sounds good. So let's rebuild this application and see how our app looks like now with all our changes. Come on. OK. OK, so that looked much faster than how it was before. Like, it was much faster than our 12 seconds, and looks like all our text code is going through our fast path, right?
Yep.
So I do have a can trace for our final version of our app. Let me bring that up and see how our startup time looks like for our final version here. So it looks way smaller than how we started, right? So I'm going to go through the same the logical activity of figuring out what our last rendering event looks like and see what our startup time is now for our application, right? So I'm going to do the same thing. I have a big layout here, and I have my rendering event here after that layout. So I'm going to select all the way from process start to that rendering event. So let's see what our startup time looks like. So we are close to 700 milliseconds, Mark. So 12 seconds to 700 milliseconds. So
we did it.
Mission
Awesome.
accomplished. OK.
Thank you,
good.
Kiran.
Good. Thank you. So I do want to pull out our memory trace too and see how our memory looks like for this, right? So let me pull out my memory trace here. Somewhere I have here my memory trace. So let me hover over this. OK, so we are at 25 megs.
Awesome
so
job,
that is pretty
Kiran.
good. So we
Awesome.
went down from 84 meg to 25 meg. And then the main reason behind that memory was those big scale images, because you had those gigantic images not getting decoded to the right size, but to the full size, and was contributing to your whole image section there, right? So with this, Mark, I do want to send it back to you and see how we compare against before and after on this one.
OK, so here's the final before and after. This is where we started and where we got to. So big thanks to Kiran for finally code reviewing my app. So here's a top 10 again. When you run into a performance problem, please use this. Please apply the techniques we showed you. Apply this. Who knows what will be the problem in your app, but you go through the whole top 10. I guarantee your performance of your app will improve. So call to action, convert to Windows Universal App. Follow the top 10 list if you have a performance problem, which we just showed you. Every release, we put out a performance white paper for XAML, and we'll do another one. You can expect it to be a deeper version of this talk, so the text version of this talk. Tomorrow, there is, Office is giving a talk on how they're using XAML, and I kind of told them, like, hey, I have this analogy. Maybe you guys want to borrow it. I think you guys are trying to convert XAML into be the Formula One racing car. And they said, oh, no, we think of ourselves as a bus, but more like a rocket bus. So if you want to find out about how Office is converting XAML or building a rocket bus with our platform, it's going to be an interesting talk. And
do you want to do a quick
yes, we thought
challenge
we would
and then see how we are?
We would close with a death match on which app is faster.
Your device versus my device, your app versus my app.
Okay, so
Okay,
on the
you
left,
ready?
on the left is
Yeah,
the,
I'll give you a head start, Mark. Go.
okay.
Go.
No, it's okay.
Yeah, no, go for it. Okay. Okay, I'm done. I'm going to go take my questions here, and you can wait for that. Thank you, guys. Thank you very much.